What percent of this molecule's valence electrons are sticks and dots? Well, right off the bat, we'll eliminate choice C, our junk answer, because 35 plus 55% sums to 90%. Sticks and dots comprise all of the molecule's valence electrons, so that has to add up to 100%. Let's make sure we're clear on the definition of percent as an equation so we can adapt it for this context. Percent of something is the number of interest divided by the total amount times 100%. For example, one of the 4 blocks is yellow, so 25% of the blocks are yellow. Here, we take the number of sticks or dots and divide it by the total number of valence electrons of our molecule times 100%. And as a point of clarification, the sticks and dots are the molecule's valence electrons. Analogously, if we calculate the number of red and yellow, we have separate calculations for each color, and they have to add up to 100% because that accounts for all the colors among the squares. And I'll admit, this is confusing, but certainly what would help us is figuring out the denominator, the total number of valence electrons in our molecule. But looking at our molecule, it's really unclear where our valence electrons are. In fact, our molecule is in bond line form, a summary model, so we'll need to convert it into a Lewis structure to reveal the missing atoms and features. If we look at this molecule up here, the ends and bends are carbons, and they may or may not have hydrogens directly attached to it. Likewise, the ends and bends of this molecule are carbons, so there are 5 total carbons for this molecule. 1, 2, 3, 4, 5. By nature of its properties, each carbon atom will form exactly 4 bonds, but it's clear that from looking at this diagram, only 2 of these carbons appear to have 4 bonds, this one and this one. And broadly speaking, that goes back to the fact that a bond line structure is a summary model that doesn't illustrate all the features of a molecule, because each of these carbons does in fact have 4 bonds. It's just that we don't see all of them. Specifically, we only see the bonds between carbon and carbon, as well as between carbon and oxygen. This carbon right here has 4 bonds like the rest, but we only see one of them. And hydrogens are going to make up the difference. So if this carbon has 4 total bonds, and we see one carbon to carbon bond, it has 3 hydrogens total. We use this equation up here to do the same for all the other carbons. The number of hydrogens attached to each carbon is the number of bonds it has, 4, minus the number of bonds we see. Using this equation for each of the molecule's carbons reveals all of the hydrogens in this molecule, and the 2 that already had 4 bonds shown don't have any hydrogens because 4 minus 4 is 0. Remember, we need to find the total number of valence electrons in our molecule, all the sticks and dots. And while we've uncovered all the sticks of our molecule, we still don't have a complete Lewis structure because we haven't revealed any dots. And the key to finding these dots lies in the fact that each atom has a 0 formal charge. How do we know they have no charge? Because if there's no charges mentioned in the diagram, we assume all the elements' charges are 0. The good news is that whenever carbon and hydrogen have a 0 formal charge, which is basically always, neither of them will have any dots. So that just leaves us with oxygen, and we can actually use its formal charge of 0 to calculate the number of dots it has. Write down this equation if you don't already have it. Dots equals group number minus sticks minus formal charge. Oxygen is in group 6, and for each of the oxygens in our molecule, it has 2 sticks and a 0 formal charge, so it has 4 dots in total. So here's our final Lewis structure. It has 16 sticks and 8 dots. And as a reminder, we found the Lewis structure to find the total number of valence electrons in our molecule. So does that mean that we have 24 valence electrons because 16 plus 8 is 24? Well, no, because a stick is 2 valence electrons and a dot is 1. So 16 sticks carry 32 valence electrons and 8 dots carry 8. Therefore, a molecule has a total of 40 valence electrons because 32 plus 8 is 40. But again, we have to figure out what percent these sticks and dots contribute to these 40 electrons. We came up with these percent equations earlier to help us, and we know that the valence electrons, 40, go in the denominator. But the question is, what exactly goes in the numerator of these percent equations? Do we use the number of dots and sticks, or the number of valence electrons they each correspond to? There's a clear explanation for why one path is logical and the other is not, but let's try both and see why one works and the other doesn't. We carry out the math, and if we use the number of sticks and dots as is, we get 20% dots and 40% sticks. But if we use the number of valence electrons our sticks and dots correspond to, we get 20% dots and 80% sticks. So we have 20 and 40 as well as 20 and 80. A is clearly the correct answer because that's the only one that corresponds to remaining answer choice. But what does that say about the math we just did, and how is that going to help us for future problems just like this? Firstly, we got rid of answer choice C at the beginning of the video because the numbers didn't add up to 100%. Similarly, if we simply use the number of sticks and dots, it would have added to 60%, unlike the corresponding valence electrons, which adds up to 100% as it should. And that makes sense because 32 plus 8 is 40 valence electrons, and 40 is 100% of 40. Another thing you might have noticed is that the values for the dots remained the same, whereas the numbers for the sticks doubled. Very simply, this goes back to the fact that one dot equals 1 electron and 1 stick equals 2.